When I introduced lists, I said they were different from tuples primarily because they're mutable. I can change elements inside of that. It's a really handy tool to have, but it causes some really interesting potential for problems. And I want to show you where those can arise and how you can guard against them. So we're now going to talk about the idea of not only mutation, but of aliasing and of cloning. Topics that are really important, a little tricky to understand, and again, go look at the Python tutor if you want some help working through this after you've listened to what we're about to discuss. But let's think about this idea. Again, I said lists are mutable. I can change them. As a consequence, not surprisingly, they're going to behave differently than immutable types. In particular, what is a list? It's an object in memory, and I have a variable somewhere typically that's going to point to that object. That's how I refer to it. That's how I say give me something at a particular index. One of the things about a list, though, is I could have multiple variables pointing to the same list. These are now clones, if you like, or copies. Actually, I'm going to say that differently. They're not yet copies. They are the same instance, but different names for them. So they're really just aliases for that. One of the things that could happen then is that if I go in and change an element of a list under one name, it also changes under the version as I reference it from the other name because it points to the same place. And that has some really potential for big side effects that can cause interesting problems for us. Let me give you an analogy. I could have a famous person, and I could associate attributes with them. That person might also be known by many different names. So they could have nicknames, and all of those nicknames point to the same person. So for some of you, here's a famous person. It's known as Justin Drew Bieber, or as Justin Bieber, or as there's a whole bunch of nicknames for this young man. And he also has some attributes associated with him. He's a singer, and he's rich. But if I add a new attribute to him, something he's done recently, all of his nicknames also refer to both the old attributes and the new ones. So that the Beeb is not just a singer and rich, he's also a troublemaker. And J. Beebs is not just a singer and rich, he's also a troublemaker. All due respect to Mr. Bieber. The point is that you share information because you have aliases or nicknames for the same structure. Same problem, same issue, same opportunity arises with a list. So let's look at a couple of examples here. I'm going to create a list, and I'm going to show you both on my computer and separately, of warm colors. So I'm going to say this is a list of red and yellow and orange. And I'm going to say hot is the same as warm. All right? In my global frame, I've actually created a binding where warm is bound to the list whose first element is the string red, second element is yellow, third element is orange. Hot, where does it point? Oh, to the same place. Because notice what I did here. I said get the value of warm, which is that arrow, and bind the name hot, to the same place. So it binds to that list. And that says, as a consequence, two things. One is if I print warm, I'm going to get that list. If I print hot, I'm going to get that list. But now, if I append something to hot, I say at the end of hot, add in a new hot color, pink. What is hot? It's that list. But what is warm? It's the same list. And that's because I literally, in hot, added this element in, and because warm points to the exact same structure, it now has changed. It has mutated. And that's tricky because I might not have intended to change warm, but only hot. Since they were pointing to the same thing, one was an alias for the other, I've had that indirect side effect that I wasn't expecting. One of the consequences of this is that print is not the same as equality. Strange statement. But what it says is even if two lists print out the same thing, that does not mean they are the same structure. And I can test that by mutating one and checking. So again, let me type this in. I'm going to give cool a set of colors. Blue, green, and gray. And I'm going to define chill to also be the set of cooler colors. Notice this is different than what I did in the previous case. In the previous case, I said let hot equal warm, have it be the point to the same structure. Here, they point to different versions of the same set of strings. And you see that right here. Cool is that list. Chill is that list. And while the names are the same, they are different structures. And so, in fact, if I look at cool, or I'm going to do it more formally, if I print out cool, it prints that. And if I print out chill, looks the same, but they're not. And here's how I can show it. Because I can mutate them, I'm going to change the second element of chill to be blue. And now if I print cool, I still get blue, green, gray. But if I print chill, I get blue, green, blue. And that's important because initially it might have looked like they're the same thing. They print the same. They are not. They point to different structures. We have to be careful when we think about what we're doing to test equality, and we have to be careful when we think about how we use elements of structures that can mutate. The third thing I can do is I can clone a list. I can make a copy of it. And so I can make a slight change in what I did earlier on, which is that I could define cool, again, to be this list of the cooler colors, blue, green, and gray. And rather than copying the same set of strings over again, I can simply say I want chill to be a clone of cool. And again, notice the difference. In the very first example, I said something like let hot equal warm. I could have said let chill equal cool, but then chill would have pointed to exactly the same list. With that colon in there, I make a copy of chill, and you can see that over here. I've got cool pointing to one version. I've got chill pointing to a second version. And that now says, for example, if I mutate chill, I append to it the color black, and I print out chill. Black is there, but cool has not changed, and that makes sense because cool is pointing to this structure. I mutated or changed that structure. Cloning lists is really useful when I want to do something with the list that involves mutation, but I don't want to, in fact, change the original list. I can make a copy very quickly and use it. And I'm going to show you an example of that in just a second. But we've seen aliasing and some of the effects of that in terms of side effects. We've seen cloning, and we've seen the fact that because lists are mutable, I have to be careful when I want to ask about are two things the same, even if they print the same way. We've already talked about this, but I want to give you one more example. I can sort a list, and I've suggested there are two ways to do the sort. I could use sort, or I could use sorted. Sort mutates the list, changes the actual structure, but doesn't return anything. Sorted doesn't mutate the list, essentially makes a new version of the list in sorted order and returns that, so I'm going to have to assign that result to a variable. And I've shown you an example here. I started off with warm as a sequence of 3 colors. I called sort on it. That's the method associated with warm. And it will literally change the order of them. And in fact, you can see over here, after I've done that, warm is now in a different order than where I started. And so I have a different structure to that. And in fact, warm now points to something different than what I really originally began with. Sorted warm has no value because sort does not return anything. If on the other hand, I set up cool as this list structure, and I call sorted on it, which I do right there, I'm going to return that to a variable name because sorted does not mutate the list. Cool will not change in this case. But what it will return is a new sorted list, and I've now created a binding that points to that structure. I'm sure somewhere along the line you're going to use the wrong version of sort or sorted. I do regularly. It's okay. But what you should see here is that if I don't mind the mutation of the list, in fact, if I want it, I can change it in place using sort. If I don't want to mutate the list, I use sorted. 2 useful tools to have associated with lists. I can, of course, have, as I already said, arbitrary structures inside of lists. So I could have nested lists, lists of lists. They might be even lists of lists of lists. One of the things that can happen here is that I can still get side effects that can occur after mutation. So let me show you an example of this. I've defined warm to be the list of yellow and orange. I've defined hot to be the list red. So I've got warm, I've got hot. And I'm going to set up bright colors to be a list of warm. And there's the formation of it with the square braces. And in fact, if I do it over here, I'm going to set up warm to be the list of yellow and orange. I said hot would be the list of red. And bright colors is just a list of warm, which is itself a list. So there's the value of warm, there's the value of hot, and let's look at bright colors. Oh, funky. 2 square braces. The outer square braces say it's a list. There's only one element in it, and that element is itself a list that has 2 things inside of it. Okay. Now, let's add something to bright colors. I'm going to say to bright colors, append at the end, hot. And I know what hot is. It is itself a list. I created that earlier on. And if I print out bright colors, oh, very nice. The outer square braces say it's a list, and notice I've got 2 elements inside of this. The first one is a list that happens to be of 2 elements. The second one is a list that happens to be of 1 element. And you can see that here because bright colors points to a list, each element of which itself points to a list. Now, let's append to hot the color pink. And if I do that, I've already added it over here. Let's see what happens if I print out hot. Not surprisingly, it's a list of red and pink. Okay, but notice the strange effect. I didn't do anything here that directly used bright colors. I didn't say do something to bright colors, but if I print out bright colors, it's changed. And it's changed again because of that aliasing or side effect. Because bright colors points to something, one of whose elements points to a list, when I change hot, which I did, I've also indirectly changed bright colors. And you can imagine this is occasionally going to cause you some difficulties if you change something you weren't expecting. We'll see that having aliases can be valuable, but we've already seen it could cause some side effects that I wasn't expecting and could lead to computations that aren't what I wanted. Finally, if I print out the whole thing of hot plus warm, I get, in this case, the nice concatenation of them. But again, I haven't changed anything inside of this structure. And I remind you that's why we want to, in some cases, use concatenation, because we want to make a version of things that are glued together rather than changing things in place. And just to show you that, if I go back and print hot, nothing has changed. It's still red and pink. One last topic about mutation, especially as you come around to doing things around iteration. If I'm going to iterate over a list, I really want to avoid mutating that list as I iterate over it. And here's a little piece of code that's intended to remove duplicates from 2 lists. The idea is if I've got 2 lists, I'd like to loop through the first list and then go over the second list and say, if I've already got a copy of that, I'm going to remove it from the first list. And I want to show you an example of this. I'm going to just type in very quickly, remove dupe of L1 and L2. And it says for E in L1, I'm going to say if it's already in L2, I'm going to remove it from L1. So there's a definition. Let's, as we've got on the slide, give it 2 examples. I got 1, 2, 3, 4 for L1. And I have 1, 2, 5, 6 for L2. And I do remove dupes of L1 from L2. And I look at L1, and it's 2, 3, 4. Wait a minute. Why didn't I remove 2? 2 also appears in L2 as well as in L1. I should have removed it from L1, and I didn't. Why? And the answer is that Python, because it's going over an iterable, uses an internal counter to keep track of where it is inside the loop. What element of the list is it going to be getting to next? It's basically saying how many times have I gone through this loop. When I mutate, which remove does, when I mutate the list, it changes the list, and it actually caused Python to never see the element 2. Because I've gone through it the first time, I've removed 1, I've mutated, it's thinking I'm going to look at the next element, but I've changed the size of the list, and the next element is no longer 2, it's now 3. So if I'm going to want to do something like this, I have a tool. I can't do that, but what I can do is make a copy. And by making a copy, by cloning the list first, now when I'm mutating L1, I've still got something that I'm iterating over that hasn't changed because it's pointing to a different structure. Again, a place where you want to be careful about accidentally causing problems because of the mutation. Just like in biology, mutation is not always a good thing. Same thing in computer science or in Python. It can be useful, but we've got to be careful about the side effects that show up.